Okay, example 4. The first thing with example 4 is it's missing the question. So what we're going to do is we're going to find A, the magnitude of P, and B, the reaction. The normal reaction between the mass and the plane. Okay, so that's what we're going to try and do. So here we've got a couple of masses. We've got one here and we've got one here. We've got them connected by a string, so there's going to be tension in the string. It's smooth, so there's no friction, luckily. And of course, it's in equilibrium, so all of our forces are going to balance. So, I start by making sure we've got a good force diagram. So we know the tension of the string. It's going to be pulling this one up here, and it's going to be pulling this one up here. The two tensions are the same. That's because it's a smooth pulley. If the pulley wasn't smooth, then there'd be some friction in the pulley, and that would cause the tension on one side to be different. But because the smooth pulley, the tension is the same. We've then, of course, got a normal reaction coming out of the surface, perpendicular to it. We've got the weight pulling down here. The first one is 3 kilograms. So this is a weight of 3g. And this one over here is a 1 kilogram weight. So we've got a mass of a weight of g. And I think that's all my forces. Then all we need to do is fill in some angles. So we can see that this here is going to be 45, right angled triangle. And actually as well, because this is a Z angle, if P is parallel to the ground, we also have that this one here is 45. Okay, so let's try and do some resolving using this. So we can resolve up the plane, we can resolve perpendicular to plane, that's for this mass. We can also resolve vertically for this one here. So if I start with the mass on this side, so let's say for the 1 kilogram mass, so that's the one over there, we can just resolve vertically. We know it's in equilibrium, the whole system, nothing's moving. So we must have that the T is balanced with the G, otherwise it'd be moving. So the tension in the string is equal to G. Not one of our questions, but I'm sure we will use it when resolving with this one. So then we move on to the 3 kilogram one, and this is going to be where all the action happens. We're going, let's try resolving up the slope first. Remember, either order is fine. Right, see what equations we get. So we've certainly got T is the force pulling it up the slope, and it's got some help from P. Right, P is pushing it up, isn't it? It's pushing it in as well, but it's pushing it up. And to get to the line of the slope, we have to go through the 45. So it's P cos 45, and that must be equal to this force downwards, and the only force downwards is from here. So if I put in the perpendicular, you can see it's pulling it down the slope. We've got through the 45, and it's a force of 3g. So it's 3g cos 45. And I will just replace that T by G. Right, of course, 9.8. Okay, and looking at that, actually, I know what G is. I don't know what P is, but I'd like to find it. And I've not got any more unknowns. So as soon as you get an equation that's only got one unknown, you can solve it. Right? It's only if you've got an equation with 2 unknowns or more that you can't solve it straight away. So rearrange this. This is P equals 3g cos 45 minus g all over cos 45. So pop that into our calculator using 9.8 for g. And we get that this is 15.5 newtons to 3 significant figures. So that's part A, magnitude of P, and then part B, the reaction between the mass and the plane. Well, that's my R on my diagram up at the top here. So again, we're just gonna read that off. So let's have a look. What have we got? So resolving in the direction of R, perpendicular to the plane. So R is pushing it up. That's actually the only force pushing it up, because this P is pushing it down into the plane, right? It's putting more pressure downwards in the opposite direction of R. So this is R equals P, and then we have to go, to get to the line of R, the perpendicular line, we have to go away from the 45, so it's sine 45, and it's also got the weight, of course, pulling it down, 3g. To get to that green dotted line here, we have to move away from the 45, so it's 3g sine 45. Right, we know what P is though, it's 15.5. I will use full calculator accuracy though when calculating that to work out my R value. So P times sine 45 plus 3 times 9.8 times sine 45. This is 31.8 newtons to 3 significant figures. Okay, and that's R and P. And that's the end of the examples for this lesson. So again, the key thing, we can only resolve, right? We can resolve on both masses. This one vertically, because that's the only way the forces are, and with the slope, up the slope, and perpendicular to the slope. The tension is the same all the way along the string. And then you just balance the forces. So the work is going to be exercise 7b, and it's going to be the odds. I just wanted to get you started though and have a look at question 1 on that. Okay, so here, just a little bit different to the example, I just want to make this point. So it tells you in question 1 a picture of mass 5 km suspended by 2 light inextensible strings, each inclined at 45. So when we make this model, right, we make this picture, the fact is that this and this are not the same string, they are different strings. If they were the same, they would both have the same force of T on them. But because they're 2 separate strings, they can theoretically have different tensions. Spoilers, it will be the same in this first question, but if it wasn't symmetrical, if we didn't have the 245, the tensions wouldn't be the same. If this was, say, a 20 degree and a 70 degree angle, one of the strings would be taking more of the force. So what we're going to do is we're going to call this one T1 and this one T2, or call them X and Y if the subscripts are a little bit too much for you, and then resolve it from there. So if it's one string, tension is the same all the way along it. If it's 2 different strings, they will have 2 different tensions.